now that you've spent a lot of time calculating the answer to this by hand, here's the answer, negative 1.6161. I'm not sure if it keeps going, the calculator seems to stop there. Now it's time to introduce you to another idea, variance. And variance, you may have heard it before, is the square of standard deviation. And I want to explore also how to do these things on the calculator. So if you go to the stat menu and you edit the data, and you fill the first list, list 1, with all the values, and the second list with all the probabilities that match those values, then you will be able to calculate the average and standard deviation for this random variable. In other words, the expected value and the square root of variance, standard deviation. The way you would do that is go back to the stat menu, calculate one variable statistics, but this time instead of leaving frequency list blank, list 1 will as usual be all the various values you can get, but list 2, or whatever wherever you typed in the probabilities, that will be your frequency list. And that basically means here's the list of all possible values, and here is how frequently each of those values will occur. Now I want to point out briefly, I want to remind you guys of the difference between statistic and parameter from early on in the course. A statistic is what you get when you're looking at a sample. So average of a sample is called x bar. Average of a population is called mu. Standard deviation of a sample is called S sub x. Standard deviation of a population is called sigma of x. Ignore the square, that should not be there. This is variance, not standard deviation. The difference is one is in a whole population, the other is in your sample. We usually take, well, at least late in the course, we'll be looking at our statistics and trying to figure out what the true parameter may or may not be. I know that 15% of my students are sophomores, so based on that I want to estimate what percentage of all students in the school are sophomores. Something like that. So, yeah, let me think for a second about how I want to present this. So the reason I brought this up is because when you do that on the calculator and you go to the stat, calculate one variable statistics, list 1 is my list 2 is my frequency list, calculate, you'll get the usual information, oh here's the average, here's the standard deviation, but some fields are going to be blank. Specifically S sub x, where we used to look for standard deviation, will be blank. And this is because these are not for statistics, these are for parameters. We're talking about what will happen in the long run of playing a very large number of lottery games, an infinite number of lottery games in a way, only we try to avoid using the word infinity because that's not real in reality, so we just say a very large number. But still, across all lottery tickets, we would expect this is how often each of those things would happen. So since we're talking about the entire population of all lottery tickets as opposed to a group of lottery tickets we looked at, we're going to be using the symbols, the Greek symbols, for parameters. So instead of calculating S sub x, all they give us is sigma x. Sigma of x, the standard deviation, is $20. In other words, while the typical result is for you to lose $1.61, your typical result will miss that by $20. That's because our our distribution of the random variable is very skewed right. You have a very small possibility of being super far away, and that will change the standard deviation to make it very large because a few very far away results bounce out against a lot of very close results to give us a medium distance from the mean being normal. And variance would be the square of that. And yes, you could calculate it by hand, what fun. Okay, $2 losing $2, that's the first result, losing $2, minus the average, losing $1.61. Okay, so that's a difference of about 39 cents. Square that, so that's a difference, instead of basically 0.4 square, it'll be about, that's about 16 cents, 0.16, times the probability, probably around 0.9, 0.15 or 0.16 still, square, and take that, and then add the next one, redo that calculation for the second one, so you sum them all together. So $18 minus this would come out as almost $20. $20 squared is almost $400, times the probability, so that comes out actually very small, only about $3 or $4. Add that to the first one, and then do the same for all of them, and then when you're done, add them all together, sum of them all, and then square root the whole result, and apparently you get 20. No, you don't get 20. You actually get something much bigger, because this is the formula for the variance, which is the square of that. So what that formula would give you would be the variance, which is about 400, and probably my guess is 401 or so. 401-ish. Yeah, the idea of variance is, if standard deviation is typical distance from the mean, then you can think of variance as amount of randomness involved here. It has a lot of useful mathematical properties in theory, but in class we won't use it that much because we understand what standard deviation means. It means we typically miss by $20. Now, will you typically miss this by $20? Usually you'll miss it only by a few cents. Occasionally you'll miss it by still less than $20. So why does standard deviation come out so big? Because it's not average distance from the, you really shouldn't think of it as average distance from the mean, you should think of it as typical distance from the mean. And as we explored months ago, a very small number of exceptional numbers has more weight than a large number of really close. It's slightly weighed in favor of those that are very far away. Just like when we had a line of best fit, or a least squares line, one point very far away from everything else would significantly affect the shape of the line. And yeah, small number of extreme points do that here also. Oh, it's vacuuming time. So, you know what? Let's pause here, and I'll get you another video in a while. Yes? Yes.